I'm really excited to be here at QCon, right here in Times Square. I'll start off with a really quick little story. 11 years ago, I had an internship at an off-Broadway theater around the corner. I was the production intern, so I was helping out with scenery, lighting, running the shows, none of the stuff that happens up here, but all of the stuff that happens behind the scenes. And I never expected to be up on a stage in Times Square under the lights, and yet here I am, and I'm here to talk about microservices. So I hope you're all ready. Is there enough energy in this room? Can I get a woo? Yeah, there we go. OK, I know it's like the middle of the afternoon right after lunch, so I just wanted to make sure everyone was awake and ready for this. So today I'm talking about no microservices in island. And one of the things that I've noticed going through a bunch of the talks that have already been at the conference is no one really defined what a microservice is. And yet you've also been hearing about these distributed systems things. So in case you're wondering, microservices are a distributed system. Just want to start that out just in case you were confused. I know there's a lot of people who were doing microservices, at least a little bit in this room. And microservices are great. We moved to microservices to get a lot of benefits in terms of agility, in terms of speed, in terms of decoupling so that we can move independently. And of course, microservices can help you cut costs by being able to scale up or down depending on your load, even though there's obviously a lot of other costs associated with them. And the thing is, when people first start doing microservices, when you have just a couple of them, you have this grand idea of what your microservices system will look at. And it usually looks really pretty, and all of the lines are straight, and they all make sense. But again, microservices are a distributed system. So as the system grows, as the system gets more complex, it's going to get a little messy. And of course, the more pieces you add, the more connections you have, something will probably go wrong. These are really big, complex systems. There's a lot of things happening at the same time. You might have multiple teams deploying. You might have teams deploying new infrastructure while you're also deploying that you don't know about because you sit over here and this other team is maybe across the country or across the world. So when you're dealing with this really large distributed system, how do you figure out when something goes wrong? How do you know what's going on in your systems? How do you even know there's a problem? And then once you've figured out that there's some sort of problem, how do you fix a problem in your distributed system? I'm not necessarily just talking about, oh, I have this one application and can't connect to the database, but real big system-wide problems. So when you're thinking about microservices, you're thinking about a lot of new challenges that you haven't necessarily dealt with if you've worked primarily in a monolithic world, or even some of the larger service-oriented architecture worlds, you don't necessarily have all of these connections to deal with. Microservices are about more than application size. It's not just about we're writing really small bits of code that get deployed independently. It's a lot more than that, as you'll see, mostly because you have significantly increased the failure points in your system. And in order to help that, your microservices need to be surrounded by an ecosystem. You don't just deploy one single microservice and call it a day. Like, we're doing microservices now, we have two. That's not going to work. Your applications have to adapt to running in a microservices-based ecosystem. And your infrastructure also has to adapt to be able to support the microservices as you grow and scale. Otherwise, you're going to be playing catch-up. I've seen this happen where you say, we're going to do microservices, you deploy a handful of services, but your infrastructure isn't there, your tooling isn't there, you're doing manual deployments that take several hours. That's not doing microservices. So when I talk about these challenges, I'm going to be talking about three specific areas. The first is deployment. How do you deploy your microservices? How is it different than the way you might have been doing them before? How do you scale your microservices? As I said, one of the biggest benefits to this large system is you can add more servers, instances, whatever you want to call them, as they're needed, rather than we always are going to have 5 servers. It's going to cost us the same amount over time. Scaling lets you scale up and scale down. And debugging. I know there was a debugging talk before this, but hopefully you learn much from both of our talks. But debugging can be a lot trickier with microservices because, as again, a lot more failure points. And all of these together help you create a foundation so that your microservices can thrive and grow. So let's start with deploying. What are the characteristics of a microservices deployment? Some of this might seem a little similar to those that are already doing it, but trust me, you'll learn more. First of all, microservice deployments should be small. If you have small services, you're probably making small changes. And one of the benefits of small changes is you can release frequently. You shouldn't be spending 36 hours running a robust integration suite for a 10-line change. That doesn't quite add up. And you also want your deployments to be consistent. If you're having small deployments that are done frequently, you want them to be done the same way every time, so you don't need to worry and you don't need to spend 4 hours. But this isn't to say, like, when I say consistent, I don't necessarily mean you should only be doing Java or you should only be doing Go. Consistent in terms of the tooling and the underlying way in which they're deployed. If you want to standardize on containers, that's great. But otherwise, your tooling should be able to support all of the different kinds of applications. So Polyglot can work with consistency as long as you build your tooling correctly. That isn't to say that you should always have a special snowflake. A special snowflake is a service that needs a different way of deploying, a different way of building artifacts, something that is completely different than everything else you do. As soon as you start having one special snowflake, you're going to have 2 special snowflakes, and then 3, and then 4. Because people are going to see that you're allowing all of these different things to happen in your system. And it's just not going to work. It's not going to scale. So what this means is you need to have really, really top-notch tooling. You need to invest in your deployment tooling. And there's entire conferences and tools out there and available for you to do this. You also need to automate as much as possible. If you're deploying multiple times a day, you shouldn't have humans touching your deploys. Again, you should not have humans touching your deploys, maybe kicking them off. But you shouldn't be going through manually uploading things, manually pressing buttons or flipping switches. It should be automated as much as possible. Now, there's an industry standard way of doing deployments that you've probably all heard about called staged deployments. This is really great for microservices because it's 0 downtime, and it allows you to roll out your changes in a way that you can feel confident that things are going right. So first, we have canary deployments. This term has been thrown out a little bit, but I haven't seen anyone yet that's quite explained it. So here we go. Canary deployment starts with your standard setup. You have the internet talking to some sort of router, which routes traffic to one of, in this case, 3 different servers. I'm going to say server, but this could be a Linux container. This could be a VM. This could be anything you put your code in and run it. But for this talk, I'm just using the word server. So for a canary deployment, you first start by deploying one single new version, and you start routing just a little bit of traffic to it. It's the canary in the coal mine, where if something goes wrong, you've only put maybe 10% of your traffic, maybe even less if you're one of the really, really big companies. And this means if you start seeing a ton of errors, you just remove the one, and it goes away, and you fix the problem, and you don't have to worry about most of the users in your system being affected. If things go well, you start replacing the current version with the new version, and eventually you get rid of the old version altogether. And this keeps you at the same number of servers as you had before, so it keeps your costs relatively stable, as well as you know that it can handle your production traffic, you know it can handle your production ecosystem, and everything's OK. The second type you've heard of, called blue-green, red-black. I know Netflix popularized the red-black thing because those were their colors. But this is a very similar deployment type, but also, I think, a little bit harsher, and you'll see why in a second. So again, standard setup. Internet talks to a router, which routes to one of many services. In this instance, you stand up a whole bunch of new servers. So you duplicate the amount of servers you have active at any one point in time. This is fine if you have 3. If you have 300, that might cost a lot of money, or if you're in a data center, you might not actually have enough servers to do that. And the thing with this blue-green deployment is at one single point in time, you do a cutover. Some of the systems allow you to do like a 50-50 split, but at the end of the day, you're left with 2 sets of servers running. I know my previous job at Capital One, we actually had to do this mostly because we always had to have a backup version. So you might have legislation or other laws in effect that you need 100% uptime, so you might need to use something like this. And the great thing about both of these techniques is you can do automatic rollbacks. You can have the system detect us unhealthy and say, I'm having 100% of requests fail, time to roll back. And of course, you can do manual intervention. But this means, so if you're automatically rolling back, that was bad. But how do you know that things are OK? How do you know a deployment is successful? We seem to throw out this term successful a lot, but no one really defines what that is. You're just like, oh, it's successful, right? And then in order to figure out that your deployment was successful and your system is healthy, what feature or tools need to exist? Because remember, we might be deploying one service, we might be deploying one application, but it's not just one application that is affected by this deployment. It could be a whole lot of things. So for your application, in order to figure out if it's a successful deployment or not, you need a robust test suite. Hope you're all writing tests. And this means both unit and integration, because one of the things about microservices that people seem to forget about is that you need to test the space between. Microservices aren't necessarily about server A is really tiny, server B is really tiny. They're about what happens between A and B. So those integration tests become increasingly important as your system grows. And of course, if you're doing frequent deployments, you need really frequent testing. So again, your test suite shouldn't take multiple hours to run. So you need to build tooling so that you can run your tests really quickly so you can deploy within a reasonable time frame. You also should have standardized health checks. There are some tools out there that just provide this for you. But within your system, all of your services should be talking the same health check language, be it port, endpoint URL, and contents. Your services also need to consume dependencies and secrets. If you're deploying really quickly and you're going from development environment, staging environment, to production environment, hopefully you're not recompiling your code every time. In fact, I would say you should not be recompiling your code every time, which means if your service needs to talk to the outside world, or if it is expecting files and certificates to live somewhere, or if it's expecting passwords and tokens, it needs to consume all of that stuff. So for dependencies, you need things like your URL to your database, URL to some third-party service, and then obviously your secrets, usernames, passwords, tokens. Hopefully the keynote scared you all into not putting tokens and passwords into your Git repositories anymore. So please avoid that. So to recap, you need your test to pass on your application. You need those health checks. And of course, you need dependency and secret integration so you can move through the pipeline really quickly. Now, what about the system? So the reason that I said standardized health checks is you need something to aggregate health checks. When a deployment is going on and you have one service going up, another service that depends on it, you shouldn't need to log into a bunch of servers to figure out if they're all passing. You should have a system-level dashboard, some sort of system-level view of the health of everything, because you want to see that system state. This is the really important thing, because as you grow your system, you're going to have servers and you're going to have applications that are much more central to the health of your system than anything else, like an authentication server. How many times do applications double check that the authentication token is valid? It happens a lot. So there are some things that if they go down, everything else goes down. You also need a bit more of a proactive system. So a fully automated deployment pipeline means that you should be confident that if something goes wrong, you're going to be alerted. We've all heard the story of the developer who starts to deploy, then goes to get coffee, and comes back, and everything is broken. In the real world, if you are doing best practices, the developer who starts to deploy goes to get a coffee should then get an alert saying something's not right, we're being rolled back, you need to go look at what's going on. So you can still go get a coffee, but you need to be ready to act in case something goes wrong. And you need to be able to see the deployment status. We don't work on teams of one usually, so usually a team will own one or more services. So if one person is kicking off a deploy, everyone on their team should be able to go and see what the status is. If you are working on something that's dependent on another team, and that team is deploying, you're seeing something weird, you should be able to go and see if that team's deploying so you know whether or not you should be expecting these errors. So having a status page that's accessible to everyone is important so that you don't have to be like, hey, person, are you deploying right now? I'm seeing weird errors, because everybody hates that. And if you really, really want to have fun in your system, we do this at Square, have some bots and deploy using chatbots or other sort of things. They make things a little bit fun, but at the same time, if every time one of your pieces of code goes out, you get a ping in Slack, you have really good visibility into what's going on. A little bit more advanced and definitely a little bit more fun, but it's something that I've definitely enjoyed since joining Square, even though I first put this in as a little bit of a joke, but I really like it now. So to recap, deployments require changes from both your application and your infrastructure in order to be determined to be successful, right? And of course, everything's going great, so you have a successful deployment, and like you're done, right? Once you deploy, you're done. You don't have to worry about anything. You can go get that coffee. Well, that's not necessarily the case all the time. Distributed systems are constantly changing. So the state of the world when you deploy is not necessarily going to be the state of the world in 5 minutes or 3 hours or the next day. So one of the things you have to be cognizant of is scaling, which is our next topic. Scaling happens when your application has more or less load. This is pretty common stuff. But how do you know that your service has more load? Do you just like log into it and see how it's doing? Hopefully you have some sort of health tracking set up so you can see that load. If you're not tracking it, you're not going to know. So for health checks for scaling, you usually want to look at things like RAM, CPU, latency, like your general, I have a server, it's talking to other servers kind of metrics. But of course, you're going to want to do something custom. If you're running a queuing system, you might want to keep track of how many items are in the queue. Because if you do a deploy, and all of a sudden those items go up and up and up and are not getting smaller, something's going wrong. Or if it's Black Friday and you're an e-commerce site, and you're having a ton of orders, and there's this giant queue of things, you need to roll out more servers to support the items in that queue. So how do microservices scale? It's a really hard question. It's actually not. It's automation. Please don't hand scale your systems. You can in a pinch, but the really great thing about automation is that you can have a smart system. It can scale up when things are under pressure, and then it can scale down when they're not. So if it's 3 a.m. in New York, and you're primarily a website that's used during US business hours, you don't need to be spending all of the time and resources keeping your servers running. So in the world of cloud computing, where you're charged by the hour, you can actually save yourself some money, save yourself some headache, and scale things down. And of course, smart systems can trigger scaling. So things like job queues being too high, RAM being too high, latencies being too high, all of these things you can control and then have scaling happen automatically. And there's two different kinds of scaling up, scaling down. Scaling up should seem pretty similar because you're just deploying a new instance, a new server, a new whatever, which is why I said all of your automation tooling should be deployed, or all of your deployment tooling should be automated, because I've seen where you have a separate deployment tool from a separate scaling tool. And let me tell you, if you have two tools, you're going to keep forgetting to update one of them. So you want your tooling for scaling and deployment to be as unified as possible. You obviously need to monitor health checks, so your system should be able to ingest the data that you're already spitting out into the world. Once instances are up, you should have something that can send traffic to them. Scaling down, again, the important thing, because people don't necessarily realize it when they're building their tooling. They spend so much time building the scale-up automation that they forget to bring the scale-down automation. So when your instances aren't being used, which again, you need to check RAM, CPU, request volume, server's getting no requests because you deployed a new version of it someplace else, you should get rid of those because you're just wasting time and energy. You need to stop routing traffic to that server and gracefully shut down. This is something that a lot of application authors don't necessarily think about because you want requests to be able to continue, right? You don't want to just take down a server and have all of the requests return some sort of error. But at the same time, you don't want to start adding new requests. And of course, you need to start disconnecting from things. You need to close your database connections. You need to just keep track of things as you're shutting down to make sure that everything happens gracefully. You need to report the progress. So your scaling automation for scaling down won't know when it's fully ready to go away unless you tell it it's ready. Because our systems right now don't necessarily have all of the insights into the individual application logic to know when something is really done being used. Zero CPU, not necessarily the best indication, because that could also be a problem. And then ultimately, these get removed. Now, I've talked a couple times about this routing traffic thing and didn't really say what I mean. Well, again, these are pieces of infrastructure that hopefully everyone in this room is at least somewhat familiar with. And I mean either load balancer or service discovery. If you're in the Envoy talk yesterday, Envoy does service discovery out of the box for you. So it's a really great thing, and I suggest you check it out. So load balancer. All cloud providers have one built in. So if you're using the public cloud, or if you have a private cloud, chances are one is already available to you. I suggest learning how to use that, because it's a lot easier than building your own or running your own. You definitely can. There are great options out there if you need to run all of your own systems. And the great thing about a lot of these load balancers, especially the ones in the cloud, is you can attach to some sort of scaling group, which is an auto-scaling group in AWS, auto-scale in Azure, and auto-scaler in Google Cloud. And you can have these two pieces talk to each other. So your Google Cloud load balancer can say, oh, hey, I need more instances because I'm getting too much traffic. It'll automatically scale things up for you. And again, it will automatically register those new instances as you have things set up. So all of that can be taken care of for you if you use a nice, smart system. Conversely, instances can go away when they're removed. Instances get removed when they're going away, just like you would expect. Service discovery, for those of you that are not familiar with it, this is something that will route to healthy instances. It's a much more centralized system, even though you can still have sidecars under individual applications, kind of like Envoy. Your applications usually register with it, or a piece of infrastructure registers for them. And you route via convention. So instead of going out and saying, I'm going to talk to this server over there, it works a little bit differently. So for service discovery, if A needs to talk to B, it'll say, hey, service discovery, get me foo from B, please. Service discovery will go to B, get it, and then route it back. But the beauty with service discovery is if B is unhealthy, and A makes that request, the service discovery returns a known error. And this is where the importance of service discovery really comes in, because you go from an unknown state, the server is returning an error. Am I just doing something wrong? Is there something wrong with the server? Is there something wrong with the network? To the service discovery said that this server is not reachable. That is a known state. It's an error. You should still investigate and figure it out. But it takes you from an unknown state to a known state, so it's a lot easier to figure out what's going wrong. Service discovery is generally pretty smart. It knows the health of your applications through health checks. And it, again, can trigger scaling automation if you have set that up. But scaling only solves so many problems, because things will still continue to go wrong. So let's talk about debugging your distributed system. First, you need to know there's a problem. Again, we're back to the how do you find problems in your distributed system? Well, hopefully you have alerts set up. No one likes getting paged, but we all do. But the thing is, you also need to know what qualifies as a problem. You don't necessarily want to alert engineers every time you get an exception. You don't want to alert an engineer the first time a request times out, because they're not going to be able to do anything. And for instance, if you're getting paged about a request timing out, and you know you have automatic retries set up, then you really can't do anything. That's a nuisance page. It should not be around. So I love alerts, but I love alerts that are actually useful even more. And what you're going to alert for varies for your application. So things like RAM, CPU latency, you can do that. Any other sort of HTTP errors you get, all of those can trigger alerts. But you also want to think of less obvious things. If your service has scaled 7 times in the past hour and you're not getting any more traffic, you might have a memory leak. That's causing your instances to run out of memory, therefore trigger scaling automation, run out of memory, trigger scaling automation, and that's something you should look into. So it's not necessarily about like your application level stuff. It could also be all of the other automation you have in the system that you're alerting for as well. You can also alert for your key performance indicators or service level agreements or SLAs. If you work in a team or on a service that is super high availability, it's important to keep track of this stuff both for yourself and for everyone else. But the thing is, alerts are for known issues. They're for things that you can think about ahead of time and think, oh, I might get a 500 error if I talk to this other server. Or there might be times when I'm trying to save a file and the disk is full. Those are known errors. But in debugging and figuring out what's wrong, there's always going to be a human component, which is why you also need some sort of dashboards. You need to be able to get an aggregate view of what's going on in your system. Again, if you saw the Envoy talk yesterday morning, there is the mention of being able to see requests with really high latencies. And until they had the dashboards, they didn't know that they had requests that every once in a while would have super long latencies. So dashboards are really important because at the end of the day, we're humans and we're going to make better connections when we visualize data than when computers do it themselves. So you found your issue. Now, how do you debug it? Right? Standard debugging 101. You're going to go look at the application that is causing the page, that is throwing the error. And oh, wait, pretend that SSH doesn't exist. This is a challenge for you all. Don't log into SSH into production, please. In addition to it being a major security vulnerability, once you stop relying on SSH and building tooling, it helps you gain much better insight into your system, and it helps you track things a lot better. So if you're not going to SSH in, use your next best thing as your logs. So hopefully you have log collection and aggregation set up on your system. And if you want to go really, really advanced, figure out a way you can configure your log levels on the fly. So being able to push a button or update a configuration file, and all of a sudden your application just starts spitting out a bunch of extra logs. This is really useful in times of crisis when you're like, oh, I wish we just had one more piece of information. Again, a little bit more work. You have to update your application, but it's really worth it if you can have the time to do it. So standard debugging technique, you look at your logs, figure out what's wrong, right? If you figure out it's a non-trivial issue and it's going to take time to fix, or you need someone else to help you fix it, it's time to escalate that up. All of this because you want to avoid cascading failures. In a really large distributed system, you don't want the failure of one application to mean the failure of everything. So there's two parts to this. The first is identification, and the second is isolation. So with identification, what parts of your system depend on another? Can anyone with really great confidence off the top of their head list out all of the consumers of the service that they run on a day-to-day basis, if it's more than like 3? It's not something that people do. It's not something that we necessarily think about on a day-to-day basis. And if you're working at a company that just is open and like any service can call any service, even if you have to go through some registration flows maybe or proxy firewall things, it's still really easy to not know who might be affected if your server goes down. And conversely, if you're the one talking to this server that's having a problem, how do you know who to talk to get it fixed? So you need to have a good idea of what's going on in your system. And this is request tracing. I know that there were some distributed tracing sessions yesterday, so do check those out if you have some time. I'm just going to briefly cover it here real quick. Request tracing is literally just following the requests as they go through your system. This is usually done with unique request IDs that are added as part of the request. These work best as an overlay. Again, Envoy talk mentioned this, and I'm going to reiterate again. If you do request tracing at the application level, applications might stomp on each other. They might forget to pass along the request ID. There's a number of things that can go wrong when individual servers are adding request IDs. So if you can do it as a system overlay, I highly suggest that. And if you don't want to use Envoy, there's an open standard called Open Tracing that has widely available tools and will help you out. And of course, if you can't do that for whatever reason, just add your header manually. It's better than nothing, is what really comes down to. Add as much as you can. and then figure out ways around it if you can't get it everywhere. OK, isolation. How do we isolate our servers? Well, this is circuit breaking. Again, circuit breaking has been mentioned, so I will briefly cover what it is. In case you have never heard of circuit breaking before or never played with it, it's really cool. It's basically a little library or sometimes an overlay that sits between your application and the rest of the world. All of your requests go through this. If it sees 200s, everything's fine, the circuit stays closed. If you start getting a lot of errors with thresholds that you can configure, high latencies, all sorts of things, the circuit opens. Again, the benefit of a circuit breaker is it lets you, sorry, I just lost my train of thought. It isolates services. So if it brings your application from an unknown state to a known state. That's what I meant to say. So circuit breaking does the exact same thing as what I talked about before, because in our big distributed system, we want our applications to be in known states as often as possible. We don't want to be dealing with stuff that just randomly fails. But another benefit of a circuit breaker is it just lets the application recover. If some server is returning 500 errors, the people running that application are spending a lot of time debugging what's going on in it. And you don't want to be hammering them with traffic, especially really peak traffic, because obviously bad things tend to happen when we have a lot of requests. You don't want those people to be dealing with a ton of requests while they're trying to figure out why something is broken. So the circuit breaker gives that other application time to recover. And this can be done at an application or a system level. Something like Envoy will do it at a system level, but you can also use libraries yourself to add it to your application if no one else is interested, or you just want to be the first one to do it. And again, circuit breakers let you fail gracefully, so taking you from an unknown state to a known state. So hopefully, your application, you figured out what's going wrong, you can deploy a fix. And of course, slowly start sending traffic. Make sure you've actually fixed the problem. Don't just open the floodgates back up if you can, because then you'll start getting paged again, things will start going back down, and you'll get stuck in this cycle of up and down, up and down, up and down, and everyone will be really unhappy. And that scaling up, hopefully, if you have your automation in place, it can be done automatically, and then alert you if something goes wrong. So all of the built-in load balancers for cloud providers and service discovery will do this for you. Otherwise, update manually. It's not the best thing in the world, but if you live in a manual world, sometimes you do have to do this. So hopefully, everything returns to normal. You've figured out the bug, you've deployed a fix, you have traffic back up to 100%. But what if we go all the way back to when you were first looking at those logs to figure out what your problem was? What if the problem isn't one of your applications? What if it's a problem in another team's application? What if it's a problem with a third-party provider? Do you have an external dependency? These are usually more obvious to us as developers because we know we're making calls outside of our firewall. We're making calls outside of our service. We're making calls to the rest of the world. Hopefully, you're aware of those. But external dependencies can happen inside your company, too. So I have 3 questions that I always ask people when they ask if they have an external dependency or not. First one, can you see logs? If you don't have access to the logs, chances are you have an external dependency. If you have access to logs, but you don't have access to source, then you can't figure out what change needs to happen to fix the problem. And then finally, if you cannot deploy a fix to solve this problem, then it is an external dependency. If you are an open company and you can see everyone's source code and you can make a PR, that's great. But you can't merge that PR, you can't deploy that PR. Therefore, it is external to you, so you have an external dependency, which means it's going to be a little bit harder to debug and get fixed. So this means you have fewer tools available. So how do you limit the impact? You have an application. It's hitting this external dependency. How do you get your application in the best state possible when you have no control over what's happening outside of you? If there's a status page you can go to for that external dependency, most third-party API providers have them, for instance. Check it. You can also, if you really want to have fun, you can monitor the status page, especially if it's something that keeps going down and you want to have an alert set up when the third party goes down. You can do that so that you know if this third party goes down, we're going to have trouble. We should proactively do something about it. But if you're monitoring the status page or you're looking at the status page and you don't see anything being reported as wrong, you need to escalate it. Hopefully you have some sort of contact with this third party, whether it's an internal person you can go to or an external contact, because you're not going to be able to fix it, so make some noise. But again, you still want to keep your system healthy. So in addition to telling someone else that there's a problem and that, hey, please fix this, we really, really want you to, you still need to take some actions on your part to keep your system great. So what is inside of your control? So we don't have logs, so we can't check that out. We might be able to do request tracing. If you work at a big company that has a request tracing overlay, you should be able to go into the system and see if it's the system you're hitting, or maybe it's 3 services down the line that's actually having a problem. I've seen in large companies sometimes one request will cause things to fan out and hit dozens of other services. So if any one of those dozens of services fail, you're going to get a failure. So it's useful for you to figure out what's going on down the pipeline from where you are. You can also circuit break. Of course, circuit breakers are one of the best tools that you have in your arsenal for making your service resilient. So you can, of course, degrade gracefully. Don't just don't just say everything's down, we can't do anything. Do as much as you can to keep as much as you can working. But sometimes your infrastructure fails. Who remembers the S3 outage in 2017? Oh yeah, a bunch of hands, everything broke. Who here was monitoring the AWS S3 status page? Oh, there's hands, that's so great. I'm so proud of you. So sometimes your infrastructure breaks, and hopefully you have things set up to mitigate that. But I know a lot of people, especially when they're just getting started with especially cloud technologies, they're like, yeah, we'll just save it to S3. It's fine, it always succeeds. It might not. So you need to take steps in your application between error handling and then circuit break as much as you possibly can to keep your applications into a known state. So to recap with debugging, your servers for internal applications, aka things you can deploy, you have source code to, you can see logs of. Log, trace, circuit break. For external applications, remember this is anything you cannot deploy. I don't care if the person sits right next to you and will likely approve and merge your PR within the hour. It is still an external dependency, because what if that person just went on maternity or paternity leave for 3 months? Who do you talk to then? You trace and circuit break. So throughout talking about all of these different buckets, there's one thing that they all really have in common. There's one thing that you've seen me kind of skirt around talking about over and over again, and that's visibility. When you're working in these really large distributed systems, it's a lot harder to see what's going on, and you can't observe what you don't see. So a lot of making microservices successful is gaining insight into them and actually seeing what's going on. And this is not free. This is something that you'll actually have to work on. This is pieces of functionality and capabilities and tools and libraries that you have to build so you can move forward and move fast and grow. So to recap, if you want to add visibility to your applications, you need standardized health checks, circuit breakers, logging, alerting, request tracing, and being able to gracefully shut down. For your infrastructure to get that visibility, you need to use health checks and make sure that you're actually using them, not just like, yeah, everything's okay, the health check returned 200, we didn't check the contents. Don't do that. Actually check the contents, because the health check can return 200, but what if the database isn't connected? I've seen it happen. You laugh. I've seen that happen. Use your circuit breakers, have pieces of infrastructure that do service discovery and load balancing, have a place where you aggregate your logs, and it's easy to see the logs from one specific server. Log aggregation does not mean all of the logs from all of the hundreds of Docker containers go in one place and then you have no idea what's going on. automate your deployments and your rollbacks, and have dashboards. Have so many dashboards. We are visual beings. We like seeing pretty colors and dots and lines. Give them to us. And again, all of this is about gathering information to create confidence that your system is healthy. You want to creating an ecosystem for microservices is totally doable. It requires a lot more metrics. It requires smarter infrastructure. And I'd like to end with a quote from the Cloud Native Infrastructure book by Chris Nova and Justin Garrison. Yeah. Infrastructure won't evolve on its own. People need to change their behavior and fundamentally think of what it takes to run an application in a different way. So thank you. I hope you all go build software to support a healthy ecosystem. Thank you.